Hello and welcome to Topic 9, Real Integrals 2. This is the last topic of this part of the course. Now, we spent the previous topic using all the tricks and tools we developed over the last few weeks to tackle some difficult integrals. In this topic, we're going to look at a final couple of examples that will draw on all that we've learned in the course so far. We'll also get more practice at constructing contours and calculating residues. In this first video, we're going to look at how to use the residue theorem for contour integrals, where the integrand requires a branch cut for analyticity. You remember from our discussions back in topic 4 that we can use branch cuts to restrict the input to a function, and this gives us single valuedness at the expense of a discontinuity across the branch cut. It's very important to bear in mind this discontinuity when piecing together the different parts of a contour. These are the intended learning outcomes for this video. After watching this video, you should be able to compute real integrals where the corresponding analytically continued complex function is multivalued. And we'll do that by using branch cuts. Let's begin.
In this video, we're going to be talking about integrals of multivalued functions. You'll recall way back in topic 4 and from our discussions there, we were looking at the complex logarithm, and we also looked at roots of complex numbers. In particular, we dug into the square root function. There we saw that we had to cut the plane to ensure function analyticity. That basically meant that we restricted the input to our function and we got a discontinuity at a cut, which we could never cross, but we got single valuedness. Now, this method of using a branch cut, this can be useful when evaluating infinite integrals of real functions whose corresponding complex functions by analytic continuation. So whose corresponding complex functions are multivalued. We'll see that we'll be able to use all of the tools that we developed in the previous topic for contour integrals where the function is multivalued. And the best way of showing this is simply to go through a worked example, and that's what I'm going to spend the whole of this video doing. So, for example, let's evaluate the real integral I is the integral from 0 to infinity of x to the p over x squared plus 1 dx. And this number p is real, and it lies between 0 and 1. Well, as usual, let's analytically continue our function, and we're now going to be looking at a contour integral. So it's the integral of z to the p over z squared plus 1 dz. And we're going to see it'll be useful to use something called a keyhole contour. And I'll draw that in a second. And you'll see why it has this name. Okay, I'm going to draw a picture. you'll spot that we have z to the power of p, where p is not an integer, and that means immediately that the point z equals 0 is a branch point. To keep it single valued, we're going to make a branch cut along the positive real axis. That goes off to infinity. I'll make a little note here. That branch cut to plus infinity constrains angles to be between 0 and 2 pi. Okay, we're now going to draw a keyhole contour. I'm going to label the various parts. This straight bit, arbitrarily close to the real axis, is A. This circular part is B. This bit returning along the real axis is C. And this bit, this detour around the branch point, is D. I'm going to make a couple of notes on this diagram. So we have minus R and R, and we're going to be taking this to infinity eventually. I'll note here that we must avoid the branch point z equals 0, and that's done with a circular detour with radius epsilon. And the last thing I'm going to note on this diagram, which is extremely important for multivalued functions, is here we can take this path A arbitrarily close to the real axis. But we must be very careful to assign the appropriate principal values of x to the p for these paths A and C. So unlike in our previous discussions where we had a channel and considering the limit of 0 channel width, the contributions cancel because they're traversed in opposite directions. Here we cannot do that because of the branch cut. A and C cannot be brought arbitrarily close together whilst still assuming continuity. We'll see the consequences of this later in this video. Okay, let's now consider the contributions to our contour integral. So we have the integral along this keyhole contour can be broken up into a contribution along A, contribution along B, contribution along C, and a contribution along D. And eventually we will be using our familiar residue theorem. Let's look at each of these contributions in turn. First of all, let's look at the contribution on A. Well, here we have that z is the real number x, because we can take A arbitrarily close to the real axis. And this means that the integral of f of z dz is going to be the limit, and we have two limits here. There's epsilon, which is the radius of that inner circle, tending to 0, and r tending to infinity, of the integral from epsilon to r of x to the p over x squared plus 1 dx. And this is going to return our desired integral I from above. You'll see here epsilon is the lower limit, r is the upper limit, and we return our desired real integral. Okay, what about the next contribution on B? Well, on B we have that z equals r e to the I theta. As we did in the previous topic, we're going to look at the behaviour of the integrand in the large z limit. So in the large z limit, the integrand, and that's at the top of the page now, the integrand is going to go as z to the p over z squared. And that's 1 over z to the 2 minus p. But you'll also see at the very top of the page that we've constrained p to lie between 0 and 1. And that means that this here, the integrand, does indeed fall faster than 1 over z, which was a condition in the previous topic for the contribution along a circular arc to vanish. Therefore, I can say that as r tends to infinity, the contribution along B vanishes. Next, let's look at the path C. Going back up to our picture, we see that the path C lies just below the real axis and just below that branch cut that we've used to ensure single-valuedness. Crucially, we have to remember that that's a discontinuity that we cannot cross, and therefore for values of z lying on the path C, we have to ascribe the angle 2 pi instead of 0. This will become clear in a second. So on C, we must be careful to remember here that z is given by some real number r, and then times e to the 2 pi I, and that's thanks to the discontinuity at the branch cut. That means that in the integrand we're going to need z to the p is given by r to the p e to the 2 pi pi. This is a very easy thing to trip up with when dealing with multivalued functions in the complex plane. You have to be very careful about assigning the correct principal values. Okay, so returning to this, we have the integral along C, and we're going to be interested in the epsilon tending to 0, r tending to infinity limits. And looking back up at our picture, C is oriented so that you start at large values and go in towards the origin. So the integration limits are this way around. Z to the p gives us r to the p e to the 2 pi pi, but then z squared plus 1, we don't have to worry about the multivaluedness. This is dr. Flipping the integration limits and taking the exponential outside the front, we can rewrite this minus e to the 2p pi I times our desired real integral. Let's deal with the final contribution, which is on D. Looking up at our picture, D is a small circular contour of radius epsilon. We can therefore assign that Z is epsilon e to the I theta. And so the integral along d of f of z dz becomes the limit where epsilon is tending to 0, and then the integration limits are from 2 pi to 0. In the picture, that's because we're traversing d in the clockwise direction. And then we're going to have z to the p gives us epsilon to the p e to the I p theta over epsilon squared e to the 2I theta plus 1. And as usual, we had to be careful with the differential. That's going to give us epsilon I e to the I theta d theta. As usual, we can set an upper bound to this quantity. This is the limit as epsilon tends to 0. I'm going to take out the factors of epsilon at the front. We have epsilon to the p plus 1, and then the integral from 0 to 2 pi of the absolute value of this. You'll notice two things as epsilon tends to 0. First of all, this guy is going to vanish. And secondly, this denominator is going to tend to 1. Together, these ensure that this limit causes the integral to vanish. So the contribution along d vanishes. Putting together these four contributions, we're left with our contour integral along this keyhole contour is z to the p over z squared plus 1 dz. This reduces to the contribution along path A, which is the desired integral. The contribution on B vanishes. The contribution along C is minus e to the 2p pi I times I, and the contribution on D also vanishes. Tidying this up, we have that the contour integral is going to give us this. The last thing to do is evaluate the contour integral using the residue theorem. And you'll probably spot that our contour encloses simple poles, and this is by finding the roots of the denominator. Z1 is plus I and Z2 is minus I. Going back to the important point that we have to use the principal values of z to the p, I'll note that to use these values z1 and z2 in the evaluation of z to the p, we must ascribe or use principal values. We're going to write z1 is e to the I pi by 2, and z2 is e to the 3 pi I by 2. And I'll note here that this is not minus pi I by 2, and that's because of our choice of the angles theta given our branch cut. Okay, carrying on, we can now look at the residues. The residue of our function at z1 as usual we'll use the result from topic 7. This is the limiter z tends to z1 of z minus z1. And then we've got z to the p over, and then we can break up the denominator as z minus z1. Z minus z2. The factors of z minus z1 cancel, and this leaves us with z1 to the power of p over z1 minus z2, and it's easy enough to check that this is e to the p pi I by 2 divided by 2i. Let's calculate the other residue. We can use the same expression, this time with z2. And here we're going to be left with z2 to the power of p divided by z2 minus z1. And using this principal value, this ends up as e to the 3 p pi I by 2 divided by minus 2i. Putting this all together, looking at the very top of the screen, we have that the integral of our function around the keyhole contour is given by 2 pi I times the sum of the residues, which we can write like this. And from the line at the very top of the page, we know how to relate this to the real integral that we want to calculate. I'm going to leave you to tidy this up yourselves, but I'll write the next step. This can be manipulated into this form. And finally, using some double angle formulae, we arrive at the final answer, which is that our real integral is given by pi divided by 2 lots of cos of p pi over 2. And we're done. We've managed to analytically continue a function to a multi-valued complex function. We've then used a branch cut to ensure that it stays single valued, and taking care with principal values, we used a keyhole contour to relate the contour integral to the integral we want to calculate, and we used the residue theorem and some final manipulations to arrive at this answer. You'll get plenty of experience using these methods in the problem sheet questions. That's the end of this first video of topic 9. Thanks for listening.